Okay, so we will continue our discussion on magnetic RAM today. Well, the reason why I chose the name magnetic RAM instead of spin transfer torque RAM for this lecture was because there are other kinds of RAMs that do not use spin transfer torque or STT. Okay, a quick recap of what STT was. Uh, Basically, this is the STT MRAM cell that we discussed so far. Magnetic tunnel junction is the core component of this device, and you have a transistor that helps with the access process for reading and writing. Now, how do you organize this cells in an array-like scenario, right? We have to have word line and bit line and other lines running across the array. We'll see that today in the very first slide, but I wanted to point out that STT or spin transfer torque required that you have to flow current through the free layer and pin layer, both for reading and writing. I hope you guys remember that, right? That's a important point to keep in mind as we dive into other technologies that are magnetic but not STT. Okay, they're non-STT magnetic, approaches. So for write operation, you needed current flow from one direction or the other, depending on which type of switching you were after. For read, you also needed current to flow through the free layer and pin layer both. This is an important point. Both of these magnetic layers will have to experience current flow through them. Okay, now this is a 3D image which I really liked because it really nicely portrayed how different word line and bit lines are routed in an array without showing the array, by the way. So you can easily visualize it or copy paste it in a PowerPoint slide and see how the array looks like. So notice this is a transistor, source and drain and whatnot. And you have the gate right here. Word line, as you see, WL, is always connected to the gate of the transistor. Okay, they basically, word lines are used to activate the access transistor. So they're always connected to the gate of the access transistor. So there you go. This is the word line, practically connected to the gate of the transistor. Now, between source and drain, it doesn't matter which one is what, because depending on the voltage applied, they will interchange. But despite having that idea, typically the line that is connected to the magnetic tunnel junction is called the bit line. Okay, so this is your magnetic tunnel junction. Notice that. So you create an upper layer. So you have a contact, and on top of that contact, you fabricate magnetic tunnel junction. And on top of the magnetic tunnel junction, you have a bit line that runs. Okay, now, for example, if the bit line runs this way, the other cell, within the same column will share the same bit line. Okay, and if the word line runs this way, you just replicate this cells like the same transistor over and over and over again, and you see how the word line is shared, right? Can you visualize this? One interesting approach would be to just take this image and copy paste it to the right and in front of it, and then you can visualize in 3D how it really looks like. But the reason I like it so much is because it shows that these layers may not be in the same metal level, and they're not, as you see. When the source line runs, it runs in a layer. Bit line could run in a different layer on top of each other. That's why they don't overlap with each other. Despite when I try to draw in 2D, it looks like they're crossing each other, but they're not. Okay, so nothing new here. One other important point that I didn't make in the previous part of this lecture was that one key advantage of STT-MRAM or MTJ based memories is that magnetic tunnel junction MTJ is, I'm going to use the term now, BEOL compatible. BEOL stands for back end of the line. Okay, I can give you some quick background on this. Transistors, when we make chips, we don't make all of them simultaneously. We make one layer after the other. You first make the bottom layer, which is the transistor. Okay, so after you make the transistor, you go up in the higher levels of metals, metal 1, metal 2, metal 3. So these are all 3D. So you go up from the transistor layer, you go up. Okay, so typically, the way people put it in the industry is that whatever you do later is back end of the line. What do we mean by the line? Think of it like a production line in a car industry, right? There is a belt, and the car keeps going from one stage to the other. And as it keeps going, you add more and more component in it. Similar to that, when silicon wafers run through the line or production line, they have the first layer, which is the transistor layer. Next step, they have the second and third and the fourth and the fifth. So basically, it's as if you have a production line, and in the back end of the production line, you add the top layers. Does that make sense? That's how the name comes in. So apparently, the higher the layers are, they tend to have more high temperature fabrication. Okay, that's how they typically design it. There is a lot of chemistry involved, material science involved in decision making. But regardless, typically, if you go higher up, you'll be dealing with higher temperature. The problem with most transistors is the materials that we need to make these transistors, they cannot survive those high temperatures. And many other memory technologies and many other materials cannot survive. What do I mean by, they're not biological entities, right? What do I mean by that? They will melt. Everything has a melting and boiling point. Some of them will boil away, okay? So it's like the temperature is so high, some materials will melt, some materials will boil away. So you cannot really use them in the back end of the line. You have to fabricate them, then create an extra layer. Remember, oxide is also a really nice insulator, not just for electricity, but also for heat. Yeah. So thermal insulator. Apparently, as you keep depositing more and more oxides in between, when you have metal one, I mean, this is a tangent, but I can just fill it in a little bit quickly. So imagine your source line and bit lines, they're not going to be dangling and hanging like this, right? There has to be some sort of mechanical support. So we fill the section in between different metal lines with oxide. Okay, we mention them as ILD, interlayer dielectric. Interlayer ILD, or in some textbook, they will say LK, low K dielectric. For the oxide inside the transistor, we use high K, but for the oxide between different metal layers, we use low K, so that it has least capacitive coupling. Anyways, getting back to the point, this magnetic tunnel junction can be fabricated on an upper layer, back end of the line. That means there are two things. First of all, in back end of the line, you can be very creative. You can make all of these underlying things in a conventional foundry, and you can have a specialized foundry that only makes the top layer. Does that make sense? Just imagine making a cake. Like somebody bakes the cake and does everything else. All you do is just put a cherry on top. Right? So you are a cherry factory. All the bakers send you the cake and you just put a cherry on top. So basically, that's exactly what you could do with MTJ. You could fabricate everything else, and you are just putting in the magnetic tunnel junction in a separate facility. Why is that useful? Because there is a significant inertia in industry in terms of going to fancy materials. And I'll show you how fancy this material is. And I'm just prepping you for that, okay? And I hope that you should be, you should be able to at least tell that, hey, this is really difficult to make just by looking at the structure. So what I'm trying to say is when you ask someone to get into a fancy material platform beyond silicon, industry typically will not like it because, hey, we spend billions of dollars getting this tool set up. We cannot just simply go to a different tool because you have more promising material. We'll keep selling DRAM for the next 50 years, something like that, okay? Delete your photos, delete your, watch your movie and delete it. We don't care. Like, we don't care how will you store it. We cannot change our fab unless you give us $1 trillion or something like that. Okay, so this type of inertia often prohibit different emerging technologies from getting into market. But if you come up with a technology which is BOL compatible, then you can pitch to this boss or CEOs of these companies that, hey, you don't have to do anything. You just design everything else underneath it. And I will set up a fab for $1 billion maybe, which will only do this extra layer. That's fine. Then hopefully it's win-win for everybody. If it works out, then both of them get to profit. If it doesn't work out, then the big company will not lose, right? I mean, all they care is basically them surviving, not the other guys. Okay, anyways, now you know, like MTJ is BOL compatible, which is a very big advantage for STT-MRAMs. Not every memory will be BOL compatible. Okay, now just to quickly show you an alternative before STT, because we're going to a technology which is more efficient than STT. Okay, so I want to show you something that is less efficient than STT first. It's so less efficient that we decided not even talk about it. Okay, so it is magnetic tunnel junction was discovered a long time ago, but people try to figure out ways to flip magnetic tunnel junction. How can you flip the magnetization, right? One approach would be, you guys probably know this already. If you have a wire that conducts electricity, when the current flows through a wire, it creates a magnetic field around it, right? And there are, right-hand rules to figure out where the, like if you put your thumb in the direction of where the current flows, and your fingers will wrap around the direction of the magnetic field, something like that, right? So it creates magnetic field. So basically, the idea was to have a separate metal line which is not connected to anything, like literally like grids. They're running like grids, and you flow current through this line, and it creates a magnetic field, and that magnetic field will affect the magnetic layers of the free layer and flip the polarization. So flip the magnetization. Making sense? Sounds very simple, and it is simple. Everybody knows how magnets work. The only problem is it required more current to flip, obviously, because you have to create a strong enough magnetic field, and there is a lot of loss in efficiency in doing so. Converting from electricity to magnetic field again electricity. So that's when STT came in, that apparently you could flow current in certain direction from top to bottom or bottom to top, and then flip from anti-parallel to parallel using spin transfer torque. That animation that I showed you, this concept was theoretically predicted by physicists, by the way. And then somebody experimented with it and found that it works. And then people started using it in actual memory and circuits, as you see. So that's what kind of killed field MRAM. We probably will never go back. So STT-MRAM is a good option, much better than this one. But it still has challenge, by the way. The current levels, you are not probably calibrated with the numbers yet. Once we see all the memories collectively, then I will show you a table of comparison. And then hopefully you'll be able to see the numbers apples to apples. You'll see the current levels for STT-MRAM is much higher than some other memories for writing, not for reading, because STT still requires enough energy to switch this magnetic layer. Now, obviously, we will move. I'll show you an alternative in the next slide. But before that, we are still within STT. I want to add a few context about STT, beyond what we have discussed so far. Okay, let's take a different look at STT-MRAM again. This is a 2D plot taken from a different source. That's why it looks different. But the first figure, the 3D plot, is, in my opinion, the best view. But you get the idea. This is the transistor. This is where the MTJ lies in a different layer altogether. So basically, you can have this taped out somewhere and MTJ separately. Now, here, take a look at this MTJ structure. Did I tell you that MTJ is not really just three layers of materials? There are many more. These are actual pictures of how MTJ looks like. I mean, I don't know, I haven't counted, but maybe 10 to 12 different layers of materials, okay? And most of these are fancy, strange materials, not elements like silicon or germanium, for example, right? So there are reasoning behind each and every stages, each and every layer of material. Oh, okay, so you're getting depolarization. Let's do this. You're getting a lot of interfacial states. Let's add this material, which will have lattice match with the other material, blah, blah, blah. Like it's a decade-long research that led to this type of decision-making, right? And this figure doesn't have any extra benefit to you, except to show you what type of metrics people use to make decisions between these two levels. Maybe imagine between A and B, these are two MTJ structures. Yes. I'm sorry, could you repeat that? This one, or sorry, here, you mean here, right? Oh yeah, sure. Yeah, let me explain that. So like I said, in our simple model for MTJ, we had pinned layer and free layer, but apparently, or vice versa, doesn't matter how you put it. But in practice, you can have multiple layers. Apparently, free layer means something with a weaker magnetic field. Pin layer means something that is really strong as a magnet and difficult to flip. Okay. Apparently, when you make this sandwich, just imagine, I mean, again, another analogy. It could be a very simple sandwich where you have two breads and egg in between, done. Or it could be a more complicated multi-layer stacked sandwich where you have two breads, yes, top and bottom, but in between you have layers of different items. That's exactly what it is. You can have different layers of material that are weaker in magnetization and different layers that are stronger. And I mean, since you asked, actually, I'm almost tempted to add one extra bit of information here. Oftentimes, there is in a recent research, there is a surge in interest towards making MTJs that has multiple levels, which I didn't tell you about. We talked about AP and PE MTJ, anti-parallel and parallel MTJ, which had high resistance, low resistance, just two levels, so that you could represent 0 and 1. Okay, now, for a second, imagine all the memory cells that we are learning about so far, they can store one bit of information, just one. If I could give you a memory that could store 0, 0 together, like 2 bits in one shot, 0, 0, 0, 1, 1, 0, 1, 1. If I could represent these 4 combinations with 4 different resistance levels, then the same memory cell could store 2 bits of information. Can you see that? So people have been trying to, I will discuss this in a greater detail towards the end of this course, but just to give you a sneak peek, people are trying to have MTJs with multiple free layers, so that you switch one, you get intermediate resistance. You switch 2 together, you get slightly higher resistance. You switch 3, blah, 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 right? The more layers you switch, the more resistance levels you get. And it's very difficult to control, obviously, but it is being proposed, it is being studied. Once you have that, imagine, I don't know whether this is it, but this could be one of those MTJs that have multiple levels, right? So apparently, by switching certain levels, you could have resistance 1, resistance 2, resistance 3, and resistance 4, which you could use to represent 0, 0, 0, 1, 1, 0, 1, 1. That is the other motivation. You know what the benefit of doing that is? Notice, all you have to do is just go up, and nobody minds going up, as long as you don't go in X and Y direction, as long as you don't increase the area. That's where you are limited. You're limited by, why do you think you are limited by the area? Because you're limited by the silicon wafer size. This is the silicon wafer, which is a 2D. So you are given a specific area in X and Y axis, but in Z axis, you can go up as much as you want. So by adding more layers, just imagine if you need to store 2 bits, you needed 2 cells. But now, simply by making this MTJ thicker, you could store 2 bits in just the same area. Does that make sense? So that is a huge motivation for people to try to even make super fancy MTJs. Okay, it's not always just for the sake of making MTJs, it's also for making them store more information. Okay, but let me explain this figure. I hope with the understanding from the last class, you should be able to at least tell me between red and black lines, which one is showing a better MTJ performance within this region, within the left. This is magnetoresistance ratio, right? MR. We talked about tunneling magnetoresistance, remember? Just forget the term tunneling, magnetoresistance. All the same. Some people just prefer to call it magnetoresistance. Do you want more magnetoresistance or not? More magnetoresistance represents better distinguishability. So the red one shows higher magnetoresistance. To achieve that, I'm willing to go from this to the other one by adding a couple of more layers. Fine, great. Nobody does it blindly, by the way. Even it's not just about the materials, it's also about the thickness. You have to tune the thickness. If it is too thick, detrimental. If it is too thin, something will go all right. So I hope you get the idea now, right? MTJ, we started with a very simplistic picture. We'll go back to the simplistic picture again. But in between, there are more material science and chemistry involved in it than we thought before. Okay, slightly more detail about how MTJs switch. So far, we discussed that you have a parallel MTJ. You basically turn it to anti-parallel by flipping. And when I say flipping, it is always 180-degree flipping, like going from completely parallel to completely anti-parallel. Remember that? But that's not how magnetic domains work. Okay, magnetic domains precess. So basically, they start from a particular direction and they gradually rotate around a 3D axis and then go to the other side. It's kind of like if you think about it in a polar coordinate system or a spherical coordinate system, it's easier to grasp. That's why in a still image, it's very difficult to explain. But if you see an animation, if you look at the pencil that I'm holding in my hand, imagine you start with parallel magnetization. And when you switch to anti-parallel, You don't just jump and get to anti-parallel, okay? You start precessing like this. Can you see this? I wish I could show. Maybe I'll share an animation of precession on Canvas from YouTube, right? It's easy. Or you could also Google it, but I'll do one for you. But at least take a look at it in class. So it basically starts precessing and gradually gets to the other direction and then settles down in the opposite direction. That's how it switches, not abrupt switching. Now, in doing so, at any point of the time when it is precessing, if you remove the current, just notice that if it was precessing, it was trying to go to anti-parallel state, but you remove the reason why it was precessing, it will go back to its ECE axis, which was parallel, for example, or anti-parallel. So depending on where it was, how much have you precessed? Have you already gone beyond the halfway mark? Then it will just get to the other side. Okay, so we have to be mindful about not just how much current we give. By the way, you remember we need current to flip magnetic tunnel junction, but it's wrong to say that, hey, I need 100 microamps current, which we basically ran with in the last class as well until now. And I told you that there is more to it. There is a time involved in it. Even if I give you critical current or more than the critical current, it will just simply start precessing. It will not flip right away. It will start precessing. So you have to make sure that you hold on to that bias stimulus as long as it is precessing and until it settles down. But in between, if you just remove it, it will go back to its preferred state. So having said that, you will see in most literature, in most research article, they will mention critical current, but as a side note, they will also mention a time. This is taken from a realistic publication, by the way. And see, all these big players, Toshiba, TDK, blah, 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 they published their data in this figure. And IEDM is actually world's top conference in devices, electronic devices, for electronic devices, okay? World's top. Just keep that in mind. So basically, this is a top-notch data that you're looking at. So notice, still with me? Okay. So on your left, we have the critical current or read current that we're plotting. This will also give you some sense of how the numbers look like. 100 microamps around that ballpark. This is the MTJ size. Okay. So if you make the MTJ smaller, notice this. This is critical current. The critical current reduces. Isn't that obvious? Okay. All right, critical current reduces. But remember, when they report the critical current, they have to also mention a time. So you have to settle a time. If you want to make it switch within 3 nanoseconds, you have to apply this much current. Okay. Let me go back and show you something. Critical current versus time. Let me show you how that really looks like. If you give a magnetic tunnel junction a lot of time, then even with small amount of current, you'll be able to switch it. But if you reduce the time, you'll need exponentially high amount of current to switch. This is how it looks like in practice. All with me? So if I want to make it really fast, you have to apply really high current. Do you want to make your memories really fast? Yes. That means we are using really high current, right? Because fast is what we need. Okay. If you want to just save energy, okay, sure. Then live with something that is unreasonably slow. Because remember, this is not a linear curve. If it were linear, then double and half, right? But it's exponential. It could lead to significant changes. Yes. I'll explain. Thank you. Thank you. Thank you. This is a great question. So are you guys all with me so far? That will be related to this diagram, which I'll explain in a second, okay? But for the time, let's just take it for granted, but I'll explain this. Why one of them is linear, one of them is like kind of constant and exponential. So, this is the diagram that I just drew. It's already there. Notice. This is your critical current. This is the time that you give to switch. So if you provide less time to switch, your critical current exponentially increases. Okay, these are all realistic data taken from sources. Transaction on TCAS stands for Transaction of Circuits and System. Okay, this is one of the top journals in the world on circuits and systems. Okay, so Obviously, as you see, I mean, if you're wondering about why we have two data, typically they're not meant to teach you, they're meant to report information. When they report data, they don't just report the mean value, they also report the standard deviation. So they're representing how much variation that you can expect, by the way. So just ignore one of them. Just look at, maybe, I don't know, maybe look at this one. This is mean value. For the sake of concept, it should do just fine. Okay. Excuse me. So what I just told you, that if you apply really high critical current, then you can switch faster. But if not, it might take a while to switch. And notice, you can go all the way from sub nanosecond to even 10 nanosecond, because this is also logarithmic scale. X-axis is also logarithmic, semi-log. Okay. Now, keeping that in mind, notice we have to mention a time that you will absolutely have to abide by. So I need 3 nanosecond for sure. Sure, let's settle a time and then see how the critical current looks like. So now once you settle the time, which is say here 3 nanosecond, look at how much current you'll need to switch. Hey, this is an interesting observation. As we reduce the size of the MTJ, your critical current reduces. Isn't that a good thing? You guys all agree with me? That means you can now switch with less current. And at the same time, you don't have to sacrifice time to reduce your current. So that's saving your power. But then, like I said, there is no free lunch. Something will come up, okay? And let's look at the other. The red dash line is basically, for the sake of comparison, this is how much current you need to switch an SRAM. SRAMs are like crown jewels of our memory. We compare everything against SRAM, right? Am I making sense? It's like I don't know if you have a cousin like that who is a really good student, and your mom compares, like, see, why aren't you like this guy? I don't know if you have ever had anything like that, but many of us had cousins like it. So SRAM is like that really, really standard cousin that everyone wants to compare against. So similarly, that's why SRAM is there. It has no other purpose. So apparently it tells you it takes around 20 microamps for SRAM to write. Compare that to STT-MRAM, which is hundreds of microamps, which is 5 times more at least. Okay, now let's look at the dashed blue line, which is the read current. Like, looked really not that interesting. Yes, if you reduce the size, its read current will reduce, whatnot. But the problem occurs when you see the difference between the critical current and read current. Can anybody tell me what's wrong here in this region that I'm marking? Which parameter will degrade? We spoke about 3 performance parameters: tunneling magnetoresistance or cell tunneling magnetoresistance. Both are the same. Cell tunneling magnetoresistance is more practical. Remember from last class? What was the other one? Read disturb margin. What was the other one? Write margin. Okay. So which parameter will degrade here? That's why we have the quizzes. Okay. Yes. No. So see, all of them are getting the same time, 3 nanosecond, 3 nanosecond. Even read is for the same amount of time. We have to make sure that we address the time properly. Same time, 3 nanosecond. But let's see how long it takes to, sorry, how much current it takes to switch. That's the question. We are setting the time. It is the read disturb margin, if you think about it. So read disturb margin was the measure of how much read current flows through the cell when you are reading, and how far are you from the critical current, so that you don't accidentally flip. Remember that? So yes, our read current is still lower than the write current, but notice, is it not getting closer? I would be more comfortable operating here, where my read current is far, far less than the write critical current. So even when I read, it's probably going to be safe. But as you head close to this region, you are reducing the difference between the critical current and read current, and thereby you are basically making it more risky. Does that make sense, folks? Okay. All right. So read disturb. So like I said, there is no free lunch. You reduce the critical current by reducing the MTJ size, but then you also reduce the read disturb margin, which makes it risky for you to read. Okay. So these slides, there has to be some take-home message. They have no meaning otherwise, honestly. because this data will change next year. They have already changed, by the way. This is taken from 2021. Things change every 6 months, by the way. Okay, so this data will have no meaning. What is meaningful here is learning about the design trade-offs. So if you are aware of the fact, let me give you a direct example. You're interviewing for, say, Micron, and they ask you, hey, do you know is it better to make MTJ smaller? Would you like to have a 10 nanometer diameter MTJ or 50 nanometer diameter MTJ? You say, yeah, it's very good because that reduces the critical current. Done, and nothing else. Is there anything else? So that means that's a clear winner. Yeah, it's a clear winner. We would love to have as small. Why don't you make it 1 nanometer then? Okay, just make it as small as you can. You see the point? If you are aware of the fact that, hey, by the way, there is a catch. The catch is this one. So they want to see understanding, because in real life, all you care about is knowing what to try, what not to try. Honestly. Okay, anyways, so there is a region within which we rely. We don't reduce the critical current beyond a certain limit. We don't sacrifice the read disturb margin at all. Okay, finally, to address the question about non-linearity and linearity of the read current and whatnot, let's look at this diagram, which is a very standard diagram. Anybody who works on spintronics or spintronic memory knows this. This is called house diagram because it looks like a house. I mean, doesn't it? You see that? Almost like a house and roof. So what is it? Remember, I have been telling you that, hey, when a magnetic tunnel junction is in parallel state, RP, anti-parallel, RAP. And RAP is higher, RP is lower. We have been mentioning that. It's as if it's a number. Maybe this is 1 kilo ohm, this is 10 kilo ohm. As if it's a constant number. It is not. Interestingly, magnetic tunnel junctions tend to be a highly non-linear device. Okay, their resistance is also a function of voltage. It's not a constant resistance, like 10 ohm, 20 ohm. You don't get a constant resistance. Okay, so this is what you get. And you could plot it with respect to current or voltage, but notice the resistance. Take a look at as I draw, because they don't typically use different color to represent. This line, do you think it represents the anti-parallel state or parallel state? So these two lines represent two different states. One of them represents anti-parallel, the other one represents parallel. Okay, let me use different colors for the sake of it. So this red one represents one version. The green one represents the other version. Which state do you think the red one represents? Anti-parallel or parallel? Why? Thank you. Yes, high resistance. Yes, it is high, but it's not constant. It's changing. So depending on which current you use to read it, it is going to change. There will be non-linearity. Okay. Similarly, for the parallel, it's not really that much changing, but depending on some MTJ structure, it can have non-linearity as well. Maybe for this particular MTJ that we are looking at for this paper, didn't change much, but other MTJs will change. But it's safe to assume that both resistance will be a function of the applied current or voltage. Okay. Now, what is going on here? So these two lines, these two vertical lines, they don't exist. They're basically just drawn to show transition. So beyond a certain current level, they will flip. Are you guys all with me so far? Okay, so if I were to draw from scratch, I would have drawn it this way. This is your MTJ, and this is your MTJ. Two resistance. And you can have a switching here. But interestingly, I mean, surprising fact is, okay, if it switches here, why are we drawing? Oh, sorry, should probably change the color. Why are you drawing this entire thing? And why are you drawing this up to, this point? Because remember, the house diagram is drawn keeping a time in mind. So this house diagram, maybe, I don't know what the number was for this particular diagram, but maybe it was for 10 nanosecond. And with 10 nanosecond, if you apply this much current, it flips. And then you don't continue beyond that. Does that make sense, folks? Okay. Okay, one other question. House diagram tells you a lot of things. This one stops and flips to the other one. But why don't we show This parallel also flips and gets to the anti-parallel. Why is that? Can anybody? You already know the answer. Think. I mean, why are we showing just this is anti-parallel, as you all agreed, high resistance. This is parallel. Why am I showing only anti-parallel to parallel read? Or sorry, anti-parallel to parallel write or switching? Why am I not showing parallel to anti-parallel switching? Thank you. Yes, remember it requires different direction of current. So as long as your current is in this direction, you are never going to have the other kind of switching. So you have the other kind of switching with the opposite polarity. That's why the house diagram is like this. Okay, it shows, okay, it will switch beyond a certain critical current only if the polarity is also right, otherwise not. Okay, so it's the same concept. For this one, anti-parallel, there will be no switching. For parallel, there is a possibility of switching if you exceed a critical current. All good? Does that make sense? Okay, this is a really interesting and useful diagram. And most MTJs, it shows 100 and 100 because they were trying to make it uniform. But for most MTJs, they're not. One of them is skewed, like here, and the other one is okay. And as I told you, MTJs have asymmetry in their parallel to anti-parallel and anti-parallel to parallel switching limits. Most of them, unless you do something really, really fancy like this. Maybe their idea was to just balance out the critical currents by doing so. So they have a motivation and objective, and they achieve it by doing material engineering. Okay. Oh, getting back to the point. When we drew this line, this read current line, why was it linear? When you apply here. So when you apply a specific current, like keep the read current constant, you get a constant resistance. Don't you think? For a given read current, if I decide that I'll always read with 50 microamp, so for that you have a constant resistance here, you have a constant resistance there. So we take that levels for our discussion, but that doesn't mean that this resistance will always be constant. As long as you don't change the current level, you have the same resistance. But if you change the current level, then you have a change in resistance as well. Interestingly, how when we discuss the read operation for MTJ, what did we do to read? Did we apply a constant current or did we apply a constant voltage? Can anybody remember that? I told you that the easier way to do would be to apply a constant voltage and let current be generated based on how much resistance you get. Okay. If you had done the other thing, like applied a constant current, then this concept would be perfect. But typically, when you apply constant voltage, your current may still change. Remember that. And that will still change. And when you actually measure it, you see some degree of nonlinearity. Okay. But we are not getting into that degree of secondary details here in this course. Okay? But at least I'm making you aware that they exist. Okay. One more thing. Keeping all of this thing aside, some additional discussion about the STTM RAM and whatnot. And if you have, by the way, please let me know if you have any questions or if something doesn't make sense after you go home and try to revise. Please don't just let it go. Don't put it under the rug. Ask me, okay? That's the best way to do, honestly, because don't clarify this now. At some point, I mean, if you decide to work on memories at some point in your career, you'll feel that, oh, I don't know something. Okay, so now switching gear to a different version of MRAM, magnetic RAM altogether, going away from STT, but not directly. So people have been trying and struggling hard to break free from STT because of two reasons. First of all, read and write conflict. When you try to make read good, write suffers. Write good, read suffers. So the first step that people took was this is a strange design. I'm not going. This is the only slide that you have about this design, but I still wanted to have it. Okay, probably not the best solution, but as you can imagine, but this is a solution. This is a really complicated 3D structure. You have a free layer. Can you see my marking as I'm drawing, or maybe change the color to something more prominent? So you have a free layer. You have a pin layer here. You have a pin layer here. So you have two pin layers. It's a very fancy structure. The idea is to, when you read through this path. Do you see that line? So you have a pin layer, you have a free layer, so it's like an MTJ. But when you write or when you flip, you don't use the same path. You use a different path right here. You use another pin layer, this pin layer, to flip. So free layer, pin layer forms an MTJ. This pin layer, free layer forms another MTJ. So as if you have two back-to-back MTJs. And you read with this path, you write with a different path. And both of these are based on STT. STT based read, STT based write. So apparently they're still stuck with STT, but they're trying to separate out the read path and write path. That was the first effort towards SRWP, SRWP MRAM, separate read write path MRAM, only to break free from read write conflict. Okay, as you can imagine, it's a very complicated thing to fabricate and use. So I'm not gonna spend it, that this was proposed back in 2011, by the way, not too long ago. But thankfully, we have a better solution. So people discovered, and I hope you are taking note of this, that as physics predicts new phenomena, engineers are quick to adapt and bring it to some sort of use case. Okay, so there was a science article on spin Hall effect, SHE, spin Hall effect. I'm happy to share all of this if you're interested. I don't want to overwhelm you with quantum mechanics lectures and whatnot, but apparently it's a fancy phenomena that takes place in certain materials, and they're very limited. Platinum, tantalum, tungsten, these metals show an interesting property. First of all, it's what they show and why they show it. If you just hear what they show, you'll be fine. Oh, great. Oh, wow. Sounds interesting. But if I make you listen to why they show it, then you'll probably be bored because, okay, it's all quantum physics. Okay. So, strong spin orbit coupling and whatnot. But what happens is, imagine when electron flows through copper or iron or other conventional metals, you don't see any difference based on their spin. I told you that electrons can have two different types of spin, up and down spin. But you never feel like, oh, these electrons are separate, these electrons are separate. They're all equal for most metals, most conductors. But there are certain conductors, like mostly heavy metals, that distinguish between spins of electrons. And what they do is when you flow current through this material, they separate them out into two parts. One, like up spin electrons go in one side, down spin goes in the other side. This is called spin filtration. And in doing so, it creates something called spin current. So let me show you one thing. Imagine you have more charge, plus 10 coulomb charge somewhere, and plus 1 coulomb charge somewhere, somehow. And you somehow connect them with a conductor. There will be a flow of charges, don't you think? If this charge can move around, like electrons, for example. Yeah, there will be a flow of charge. That's the charge current. This is called charge current. When you have a difference in charge, there is a tendency to have a charge current. But if these charges are stuck, then it cannot flow. But if they're allowed to flow through a conductor, they will. That's how batteries work. If you connect two ends of the battery, there will be a flow of current. Okay. Now, imagine you have plus 5 coulomb here, plus 5 coulomb here. But yes, apparently there is no charge difference. But somehow you manage to have all upspin electrons here and all downspin electrons here. Okay, and somehow you connect them. Now, there shouldn't be any charge current because charge is equal, but there will be a flow of electrons still because there is a difference in spin. Am I making sense? So if there is a spin dependent flow of current, that's called spin current, and otherwise it's charge current. It's a very unique phenomena, and not too even 20 years ago, people didn't even know that it worked or it existed. Okay, so new phenomena are discovered every once in a while, and people try to make use of them. So this is what spin Hall effect, or the other name of it is Rashba effect. Engineers said, hey, okay, I don't care how it happens, you guys figure it out, write your maths and whatnot. Let me use it somehow because I have a problem. The problem is spin transfer torque takes too much energy to switch. I really like this device, honestly, and pay attention to it. It is probably going to be one of the more futuristic memory devices that has a lot of promise. Can you pay attention to this? Okay, let's do it. Okay, so you have two transistors, 1 and 2. You have a write path. This is your write path. This is your read path. I'll start with read path because you can easily relate to it. Let's see. You have a transistor, you have a magnetic tunnel junction, and you have a source line. Is it not like a STTM RAM? Is it not like a STTM RAM? Basically, an STTM RAM. You still use the same concept. When the magnetic tunnel junction has parallel magnetization, low resistance, anti-parallel, high resistance, you sense the current difference. That's how you read. Same concept. But how do you write? That's where the difference comes. So you fabricate the MTJ on top of a heavy metal layer. And that heavy metal here is tantalum. It could be tungsten, it could be platinum or something else. Okay. And then you have a transistor. This transistor flows current through the tantalum. That's where the difference is. They don't inject current through the MTJ to switch or flip. It flows current through the tantalum. And tantalum separates out the spins. And it injects a specific spin electron closer to the magnetic material here. And that those electrons magnetically switch this free layer. Am I making sense? There is no spin transfer torque like we saw in the animation that I showed you in the very first part of the STTM lecture, because they don't get injected directly. But this tantalum, when you flow current through the tantalum, it creates a spin separation, and that's one of the spins affect this magnetic layer and flips it. Very high level description. Okay, this is taken from the original paper, and this is an animation this is a 3D structure that I made. Because I felt like it's easy for me to explain this way. But anyways, let me show you this one as well. This is the transistor. This is the SOT layer, what they call it. SOT stands for spin orbit torque. This is the reason behind what happens, basically. This is the reason behind spin separation, spin orbit torque. Okay, spin orbit coupling is the reason why when current flows through heavy metal, they separate in multiple spins. So you flow current through it, and then you flip this MTJ with this current. Okay, and when you read, you use the or sense, whatever. They use different terminologies. Sense and program instead of read and write. Am I making sense? Okay, but it's all the same. I recommend that you just stick to this one. It's basically more close to our STTM RAM structure. Okay, I think these 3D structures will do justice. This is STTM RAM. This is, let me show you. This is a comparison between 1T1R STTM RAM, which you have learned so far, and 2T1R SOTM RAM. Why is it 2T? You have two transistors and one MTJ, so 1R. Does that make sense? You have an MTJ, you still have an MTJ, but what is the difference in this MTJ? You have an HM. HM stands for heavy metal. With the MTJ, you have a heavy metal layer, which you didn't have for STTM RAM, okay? So this is the first difference. The other difference is schematic. Well, the schematic looks, if you look at this part, it looks similar. But if you look at it collectively, there are differences because one of the transistors will be used to only inject current in the heavy metal layer. You see that, folks? And the other is as is for reading. Okay, the 3D structure will show you the difference. This is the transistor we just saw. MTJ could be at the upper layer. Similarly here, there are two transistors. Notice, no matter how many transistors you have, you always make the transistors in one layer. This is known as FEOL, front end of the line. Give me like 15 seconds, please. Okay, front end of the line. You make them first, and then you make the other ones on top of the transistor. So both of these transistors here and there are here underneath. That's why you have two word lines, not one. Word line read, word line write. So two word lines. When you read, you activate one. When you write, you activate the other. And source line and bit line are pretty standard. The other difference here is, can you see that there is an extra material layer needed? This is heavy metal. You see that? Connected with MTJ. Okay, don't worry. We are out of time. I don't want to rush it, but at least wanted to finish this concept that this is how the 3D structure looks like. It's a little bit more complicated to make, but you are doing all of these in what? BEOL, the back end of the line. So people don't care that much. The only challenge here is you are using more area underneath. Okay, but you're gaining a lot. And we'll talk about what you're gaining in the next lecture. Okay, we will discuss this area implication in detail in the next lecture. Thank you.